In a piece of groundbreaking discovery, astronomers have found the closest black hole to us so far. It's a part of a binary system, with a sun-like star orbiting it. Initially, astronomers thought it was just a regular binary system of two celestial objects. But when they studied the star's properties and how it goes around the black hole, they quickly realized something unusual was happening there. They had never seen a black hole and a star locked in a binary system like this before. This discovery has led us to an entirely new concept in astronomy that we didn't know before. So, how did astronomers find out it's a black hole in that system? What's so special about the closest black hole we have discovered to date? Finally, and most importantly, what has this discovery contributed to physics and astronomy? For this discovery, astronomers used data from the Gaia mission. Gaia is a silent contributor to the world of astronomy. It's not as popular as the James Webb Space Telescope or the Hubble telescope. It's unknown to many, but Gaia has changed the course of astronomy in the past few years with its extensive sky surveys. It's a space observatory of the European Space Agency and was launched in 2013. Gaia creates a three-dimensional map of the Milky Way through astrometry, which involves precisely determining the locations, speeds, and trajectories of stars and other astronomical objects to understand their origin and future in our galaxy. Gaia shares its place with the James Webb Space Telescope as it orbits the Sun 1 million miles away from Earth at the L2 Lagrange point. Since its launch, the observatory has released 3 data sets, the latest one being in 2022. Through these data sets, Gaia has revolutionized astronomy, as many research papers are published each day based on its data. Gaia found a unique binary system of a sun-like star and a black hole in its 3rd data release. Informally, the source is referred to as Gaia BH1. The binary system lies at a distance of about 1,500 light-years from Earth. It comprises a stellar mass black hole 10 times more massive than the Sun and a G-type main sequence star of 1 solar mass. In stellar astrophysics, stars are classified into 7 primary spectral classes based on their surface temperatures: O, B, A, F, G, K, and M. The O-type stars are the hottest stars, with surface temperatures greater than 30,000 Kelvin, and the M-type stars are the coldest of all, with temperatures ranging from 2,400 to 3,700 Kelvin. One can remember this order with a classic mnemonic: "Oh, be a fine girl, kiss me." According to this classification, the temperature of a G-type star like our Sun would be between 5,200 and 6,000 Kelvin. So astronomers found that the star in the Gaia BH1 system is a G-type star with a surface temperature of about 5,850 Kelvin, close to the Sun's temperature of 5,778 Kelvin. And since its mass is equivalent to a solar mass, the star is an identical twin of the Sun. Another peculiar thing that astronomers noted was that there was no significant mass transfer between the black hole and the G-star. Hence, it's a dormant black hole that emits no X-ray radiation, making it even more difficult to detect. This brings us to the next question. How did astronomers discover the system's central object is indeed a black hole? It could be a dense neutron star or a white dwarf, both of which have low luminosities and are difficult to detect. The answer lies in the nature of the star's orbit. Astronomers deduced 2 interesting facts about the binary system by observing the star's motion in its orbit caused by the gravitational pull of the dark object, the orbital shape, and the orbital period. Look at this illustration from the research paper. The expected motion of the G-star in the sky over 6 years is shown in the left panel. The middle panel depicts the star's motion around its center of mass, or the barycenter after parallax, and proper motion are removed. The final panel depicts the star's trajectory based only on Gaia's astrometric solution. Its orbit around the unseen companion is clearly elliptical with high eccentricity. In mathematics, eccentricity is the measure of an orbit's deviation from being a perfect circle. Its value for the G-star is 0.45, twice that of Pluto's orbit in our solar system. The elliptical orbit of the star revealed a period of 185.6 days. Using these data, scientists calculated that the central dark object's mass is approximately 10 times that of the Sun. But how can we be so sure? The same calculation could sit right for 2 lower mass black holes, 5 neutron stars, 10 white dwarf stars, or 200 brown dwarfs at the center instead of 1 stellar mass black hole 10 times the mass of the Sun. The answer is dynamic stability. The presence of more than 2 objects within the G-star's orbit will make the system dynamically unstable. So, it was determined that the unknown partner is either a single stellar mass black hole or 2 compact objects, but most likely black holes. Another interesting thing to note in the G-star's eccentric orbit is the wobble. Only dark companions could generate such an extent of wobble in comparison to a luminous object of the same mass. As a result, the existence of a black hole was proven. But this is where things start becoming unusual. The newly discovered binary system turned out to be an oddball or rare case. Look at this graph between the mass of the black hole and the orbital period of the star locked within the system. Compared to known binary systems containing a black hole, Gaia BH1 stands distinct. Its features are similar to NGC 3201, a globular cluster with an entirely different evolution channel, making their comparison meaningless. And this is a huge problem. Why? Because its isolation from the other binaries implies that no standard binary evolution model could explain the origin and properties of this system. So like every good scientific discovery, this one has posed some interesting questions to us. Astronomers have come up with some ideas to explain the system's evolution. The first is the common envelope evolution model. The black hole has a mass 10 times that of the Sun, so its progenitor, the star that collapsed into this black hole, must be larger than the G-star's current orbit. This means that the G-star may have been engulfed into the progenitor's gas envelope, spiraled through it, and ultimately ejected it. This hypothesis sounds interesting, but the problem is that it's improbable that a 1 solar mass star could have ejected the gas envelope of a highly massive black hole progenitor. Also, the size of the G-star's orbit is much wider than what the common envelope model predicts. The binary evolution models we have so far also suffer from similar challenges. Another hypothesis is that the system formed dynamically in an open star cluster that eventually dissolved. However, the best hypothesis that explains the system's evolution is the triple star system model. In this model, the G-star was initially a tertiary companion to a close binary system of 2 massive stars. Their interaction prevented them from becoming red supergiants, resulting in the eventual formation of a 2 lower mass black hole binary system, with the tertiary G-star companion existing in a somewhat tighter orbit ever since. If the system is a binary with a G-star and 1 black hole, in the future, the G-star will become a red giant, resulting in the accretion of mass by the black hole, and the system will end up becoming a white dwarf and black hole binary system. But suppose it is a triple object system with an inner binary of 2 black holes and an outer binary with a G-star as the third companion. In that case, the evolution may be disturbed by the merger of black holes, disrupting the outer binary. The discovery of the closest black hole with unique properties suggests the existence of plenty of such binary systems with dormant black holes in our galaxy. The future data releases from Gaia will facilitate the discovery of many more dormant black holes.